Welcome to this explainer. Today we are channeling a very specific energy. Think of the disciplined mind of a samurai, ancient warrior wisdom meeting modern exam strategy. Because when you walk into your Cambridge computer science exams, whether you're sitting for syllabus codes 0417, 0478, 2210, or 9618, you need to be able to slice through complex questions with absolute precision. We're creating a strategic blueprint for mastering the paper, focusing specifically on a foundational yet incredibly tricky topic, binary addition and overflow reasoning. Listen, we aren't just going to learn the raw math today. Anyone can memorize binary place values. Instead, we're going to learn how to explain it exactly the way the examiner wants to see it, so you never leave easy marks on the table. Let's get right into it.
So, here is the ultimate challenge. It is incredibly frustrating, right? You walk into the exam room, you understand the mathematical theory perfectly, you can add those ones and zeros in your sleep, yet you still miss out on top marks. Why does this happen? Well, let me introduce you to two classic types of students we see all the time. First, we have Alex. Now, Alex overloads every single answer with raw computer science facts, but includes absolutely no analysis. Alex will write a whole paragraph about what a byte is, but never actually answer the question. Then we have Sam. Sam rushes. Sam completely misses the command word requirements, sees the word binary, panics, writes, "It breaks," and moves on. If we look at their flawed answers with the examiner's red pen marks all over them, a harsh truth is revealed. Students lose marks because their answers rely on generic labels and isolated facts instead of precise reasoning. You can't just recognize a concept, you have to truly understand it, and most importantly, successfully apply it to a specific digital scenario. To fix this disconnect, we're going to walk through a bulletproof framework today. We'll start with the examiner's perspective, move through a disciplined answering path, introduce a 3-pass revision cycle, and wrap up with a practical memory structure. Let's move straight into Section 1, the examiner's mindset. This is absolutely crucial, folks, because it's all about moving beyond rote memorization. This comparison brilliantly illustrates the trap so many students fall into. Generic responses, just floating around like abstract clouds, rarely gain full marks. What examiners are actually looking for are context-anchored responses. Top-tier answers take a technical explanation like why an overflow error occurred during binary addition and anchor it to the specific scenario provided. To do this, top students use a secret weapon, the PEAL framework. That stands for Point, Evidence, Explanation, Link. You make your point, provide the technical evidence, explain how it works, and link it back to the question's context. If the exam mentions a robot, a school network, or a database, your answer must stay inside that world. You have to explain what the overflow means for that specific robot. Now, I want to test your examiner mindset. I'm going to give you 30 seconds to think about this. If I say an 8-bit register cannot hold a 9-bit result, which part of the PEAL framework is that? It's the evidence. Before we continue, subscribe to our YouTube channel Ace the Exams at @acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Now, what's really interesting here is that the theoretical foundation of binary operations and computer science in general depends entirely on distinguishing between easily confused concepts. Look at these common mix-ups. Our source notes that mistakes frequently arise when learners confuse things like memory and storage, or validation and verification, or, highly relevant to our topic, confusing logic processing with arithmetic processing. This is exactly where our friend Alex goes wrong, dumping facts about memory when the question asked about storage. To perform like a top-tier candidate, your notes and your studying must train you to compare these ideas, not just explain them as single, isolated topics. You have to know the boundaries of each concept. Which brings us perfectly to Section 2, the disciplined path. This is a 4-step methodology for reasoning through absolutely any question. So, the crucial point is that we need a structured methodology to analyze these concepts without panicking on exam day. You must follow this disciplined path, what I like to call the computer science success blueprint. Step 1, identify exactly what the task is testing by decoding the command words. Step 2, classify the relevant data or hardware. Step 3, explain the process clearly in sequence. And Step 4, connect it to context. Let's do a live transformation right now. Remember Sam's rushed answer about the system breaking? Let's fix it. Step 1, the requirement is to explain an overflow. Step 2, we classify it as an 8-bit binary addition issue.
Step 3, we explain the sequence. The addition of two 8-bit numbers results in a 9th carry bit. Step 4, the context. The 9th bit exceeds the 8-bit register's capacity, causing the robot's movement calculation to fail. Boom! Red marks transformed into green check marks. That is how you use the Peel framework and this 4-step path to secure maximum points.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's jump into a quick interactive workshop. Challenge number 2, find the flaw. If you skip our disciplined steps, you risk taking these classic wrong turns. The real mark killers are naming a device without explaining how it works or giving an advantage with absolutely no underlying reason. Listen to this flawed sample paragraph. The system uses binary addition. It got an overflow error, which is a disadvantage because it's bad. Did you catch the flaw? It's that last sentence, giving a disadvantage with no reason. The examiner doesn't just want to know that an overflow is bad, they want to know the mechanical reason why it's bad and what happens when that error breaks the system.
Knowing those pitfalls is great, but let's move to Section 3, the 3-pass revision cycle. Let's look at how you should actually be studying this material to ensure it sticks permanently.
A strong revision cycle requires 3 distinct passes. The first pass secures your key definitions and contrasts. What is an overflow? How is it different from a standard carry bit? The second pass is where you rehearsed worked explanations, drawing out diagrams to prove the math. And the third pass is the absolute game changer, focusing on exam adaptability. This means intentionally changing the scenario and forcing yourself to justify your choices. Let's do a speed writing challenge right now. You have 30 seconds in your mind to write one perfect Peel paragraph explaining an overflow error in an 8-bit system. Go! Point. Overflow occurs when a value exceeds register capacity. Evidence. Adding 11111111 and 00000001 requires 9 bits. Explanation. The CPU only has an 8-bit register, so the 9th bit is lost. Link. Therefore, the calculation becomes wildly inaccurate. That is how you build adaptable skills.
Let's see how this builds our understanding of real-world transfer. Why do we care so much about an 8-bit overflow? Because these exact same patterns appear everywhere in the wild. They appear in your smartphone, in industrial control systems, in banking, and robotics. Let's do a quick data scan challenge. Imagine a complex data table showing transaction processing in a bank. If a banking system experiences an overflow error during a massive financial transaction, the consequences are literally disastrous. Money could just vanish. Seeing how these patterns transfer to real-world systems helps you remember the reason for using a concept, rather than just memorizing its name from a textbook like our friend Alex does. It makes the abstract math incredibly real and tangible.
This brings us to Section 4, the 4-prompt memory structure. If you struggle to recall information under pressure, this is your ultimate retention tool. I absolutely love this framework. Think of this as your cheat sheet recap. If you want a reliable memory structure for binary addition and overflow, or literally any topic in computer science, you just need these 4 prompts. What is it? How does it work? Where is it used? And why is it better or worse than an alternative? If you can answer these 4 prompts aloud right now, your knowledge is officially ready. Let's tie this into our final system. There are 3 rules that guarantee top marks. Rule 1, command word decoding. Know what the prompt is actually asking. Rule 2, Peel framework application. Structure your answer perfectly. And Rule 3, the time management matrix. Allocate your minutes based on the marks available. If you stumble on one of these prompts, you need to go back, look at a key contrast, and try a scenario-based question again.
As we wrap up today's explainer, I want to leave you with a provocative question. What does your final pre-submission checklist look like? As you sit down to prepare for your next past paper, ask yourself how you will actively apply these frameworks. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Master that checklist, and you won't just understand the theory, you will master the paper.